Welcome friends, I am Tanmoy. I welcome you all in the channel Chemistry, the Mystery of Molecules. So this is a continuation lecture of Pinacol Pinacolone rearrangement. Previously I have uploaded basic videos about Pinacol Pinacolone rearrangement and some example. I suggest you please go through that. After that you come to this video because this is based on a selected topic that is Pinacol Pinacolone rearrangement for epoxide. Yes, I repeat epoxide because Pinacol Pinacolone rearrangement we have done in case of this glycols. Glycol means 1,2-diol, okay, and epoxides are the dehydrated version of glycol, okay. So this thing we are going to learn, and this factor I shall explain based on these examples, and it will help you to understand these unique examples. So let's start. So this is actually 1,2-diol are called pinacol, okay. So this pinacol, if it is dehydrated, for example minus water, then epoxide is produced. Okay, so this is epoxide. So this is. So here you can see one example, that is ethylene oxide. Okay, this is ethylene oxide obtained from epoxidation of ethylene. So this ethylene oxide undergo heat. In presence of heat, it converted into acetaldehyde. Okay. So how this is happening? Okay, fine. So this is happening because, so first just think that this epoxide, this is CH2, this is CH2. Fine. So what happened? It opens. So if it opens, as we know that oxygen is more electronegative atom, so it is expected that the negative charge will go on the oxygen. Fine. So if negative charge go on the oxygen, it will produce this here CH2 unchanged O minus and this CH2 plus. So like Pinacol Pinacolone rearrangement, you can see there is hydrogen which is capable to migrate, and there is oxygen which can push its electron, and this will migrate. So what will be there? It will be this double bond, this CH, and this is CH3. Nothing but this. This is acetaldehyde. Now the question is why this reaction happens. The reason for this reaction to be happen. So first of all, you can see from a cyclic compound to a open chain compound is produced. Fine, cyclic compound to open chain. So entropically, this is positive. So delta S is positive. Fine. So entropically, this is positive. Second, you can see 2 CO single bond is getting broken, and 1 CO single bond double bond is produced, and we know that the combination of 2 CO single bonds energy is lesser compared to 1 CO double bond. Okay, fine. So delta H wise, this is positive. Sorry, not positive, since this is negative. So more stabilization. So that's why this is negative. So this cyclic compound, this 3-member ring, okay, is converted into open chain. So ring strain is released. Ring strain released. Okay, so these are the factors happening in this, and if we carefully analyze this factor, we can see that delta H, delta G, which is the free energy change for a reaction, is delta H minus T delta S. This is the Gibbs free energy equation. So here delta H is negative, delta S is positive, but due to minus, this is also even more negative. So overall delta G is also negative. So that is the reason how this reaction is happening spontaneously. Okay, so this is the actual explanation for the spontaneity of this reaction. Okay, fine. So here the epoxide opening is thermal, heat mediated. Now as we know that in case of Pinacol Pinacolone rearrangement, you have observed we need acid, and Pinacol is a diol. So after protonation to the alcohol, what happens? Water molecule eliminates and carbocation is produced. But here, as I told earlier, that epoxide is a dehydrated version of alcohol, so that dehydration part is counterbalanced previously. Now the formation of carbocation. So epoxide can generate carbocation using as protic acid, proton-based acid, or Lewis acid. Both can do the same job. Here proton is consuming the electron, and in case of Lewis acid, the vacant p orbital or empty p orbital is acting as a center to accept the electron. In this case, BF3 is that candidate. Actually, it comes in the ether complex because BF3 is a 6 electron species. I know you will say that okay, there is some electron back donation from fluorine to boron. I agree. That stabilizes the electron density of boron somewhat, but it doesn't mean that this boron is not electron deficient. It is electron deficient, 6 electron species. So in order to counterbalance its electron deficiency, ether is taken. That could be diethyl ether, that could be THF, whatever. So in this way, this is. So initially the complex comes in this way. So what happens? See, this is the oxygen, sp3 oxygen donation, and epoxide is also sp3 oxygen. So similar. So what can happen? This BF3 could be coordinated with the epoxide. Okay. So this is coordinated to the epoxide. Fine. And as I told that now it can break because oxygen is donating electron to this. So oxygen is getting a formal positive charge and boron is getting a formal negative charge. Fine. Now, oxygen, since it's an electron negative atom, it will not prefer to a light to have negative positive charge on itself. Consequently, bond break. Now, question is here: which bond can break? This part can break. I mean, if this part breaks, carbocation will be generated this center. If this bond breaks, and if this bond breaks, carbocation will be generated this center. Okay. So this will break because the produced carbocation. What do I say? As always, I suggest in such cases try to draw the structure as it is. It will reduce the chance of mistake. Fine. And carbocation will be generated at this carbon. Why? Because if we see the other is this, and this is actually a primary carbon. Okay. So carbocation is a primary carbon, so it is not that much stable. But here the carbocation is produced, it's a tertiary carbon. 3 degree carbon, so more stable. And secondly, here 2, here 2, here 2, 6 hyperconjugation structure are possible. 6 hyperconjugation possible. Okay, so that is the reason this is more stable. So okay, we have understood that this will break. So fine. Now what can happen? Now this carbon has hydrogen as previous. This hydrogen. So actually I am showing this bond, but mainly the electron density is on the oxygen. So what happens? This can push here and this hydrogen can migrate there. So in this way the charge will be balanced, and ultimately if it does, then there will be a C double bond O here. Here will be a C double bond O here, and the hydrogen will go. What does it mean? This is a cyclohexane and next carbon aldehyde. So in this way this cyclohexane carboxaldehyde is produced. Fine. Fine. So similarly, like boron, we know that magnesium 2 plus can also act as a Lewis acid. It is true. So that is the reason here that next example. What do I mean? Example number 3. This magnesium bromide is acting as a Lewis acid. Just keep it in mind that epoxide is going to aldehyde. So in this way, it will help you to understand the problem in details. Okay. So you can see it's a diphenyl, means diphenyl epoxide called diphenyl ethylene, you can say. Okay, so what happened? Magnesium coordinates here any one of Lewis acid. Actually magnesium 2 plus. You don't need to think about Br because Br has do not no role except maintaining the electron neutrality of the center. Fine. So okay. So after coordination, then it will be broken. So after coordination, this will have a positive charge on this oxygen, and the electron density will go on the magnesium. So we can think the factor in this way delta positive. Let's consider, and here the actually not delta negative, there will be a reduction in positive charge density. Fine. So delta positive. So here since it's a symmetrical substrate, so breakage from equal side is breakage from both sides is equally probable. So what happened? Left open. So if it opens, it produces this hydrogen. This is hydrogen and this is pH, and this is O minus with magnesium 2 plus coordinated, and this is the positive charge. This is benzylic carbocation. This is benzylic carbocation. So we know that benzylic carbocation is resonance stabilized. So similarly, it will be resonance stabilized. Along with that, one hyperconjugation hydrogen is present. That is possible. Fine. Okay. So next, what happens? See here, one carbon, 2 phenyl. It indicates that this phenyl will migrate. But in previous video, I have explained the migratory aptitude of hydride is more than phenyl. But why this is happening? In this case, this is happening. This is a fact. So frankly speaking, I do not have the proper explanation, but this is the experimental value result. So what happened? This phenyl is migrating. So if it sorry, I made mistake. Not this phenyl, another phenyl. This phenyl is migrating. Fine, because this is it will push its electron density. So what will be the product? In one carbon there is a phenyl. There is one hydrogen, and along with that, this is a OH coordinated with magnesium 2 plus. Fine, and after removal of this magnesium 2 plus, it produces this aldehyde. Fine, same. So this much we have understood, and I believe these are fairly easy example. But the main difficulty comes from example number 4. Okay, why this is difficult? Because here you can see ring contraction is happened. So how we can explain? Means it is this epoxide is attached to the ring directly, not the extension. And in case of extended double bond, we have seen that aldehyde is formed. But how this is happening here? That is the main question. So as like other explanation for previous examples, here also the epoxide will act as a Lewis base to coordinate to the magnesium center. Fine, let's consider it in this way. Fine. So if you think normally, you will not be able to solve this problem. So for that reason, it is essential for you to think about the chair conformation of cyclohexane. And what about the epoxide? This is one cyclohexane. Let's draw another one cyclohexane. So when ring is formed, ring means same side, same direction. Okay. So what can happen? Cyclohexane can have this or this. Means by saying this, I am saying that epoxide is same side. Means this oxygen is attached from this axial side as well as this equatorial side. Okay. And if epoxide forms in this way, then it is axial. This is so same. Just this is upside, this is downside. This will be the nature of epoxide. Fine. So now let's consider that one example. Let's consider that this is coordinated to the magnesium 2 plus. Okay, fine. Now what can happen? One will open and another will attack. Okay, fine. Now see, here opening, if opening happens from this side, then this hydride can migrate. But actually this is not. Instead of that, what happens? Opening happens from this side. Okay. This side, and this bond is relatively weaker. I believe, it's my personal opinion, that this bond pair may be delocalized to the anti-bonding orbital of this little bit, which makes this little weaker. Otherwise, from energy point of view, both are same. And here there is, you can argue that okay, there is one hydrogen, that I believe this is less. But this is completely my personal explanation. I didn't read this in anywhere. Just I made by myself for my understanding, and I am sharing that information with you. So fine. Okay. So from this we have understood that this part will break. So if this part breaks, then you may think that okay, this will form. This is a minus and this is plus. Now we know that hydride migrates. Actually, where is the hydride? The hydride is here. This equatorial hydride can migrate here. But for a migration, some orientation essential. Okay. So compared to hydride, this can migrate efficiently. I will explain this in again. Let's see. So you can think this factor in this way. What I am saying, this is the epoxide and here is the hydrogen. after coordination, magnesium, these two bonds, means these and these both are weakened, means these and these both become weak, means these and these both. So what can happen? This bond can come, push, and this can open. Okay, so not a classical carbocation type. So what do I mean? How this you can explain? Similar like this, that the HOMO of this bond, this is the HOMO is here in between, and the LUMO, that is the sigma star, is here. So they can form a bonding interaction with each other, and that is the reason, that's how this forms. And this factor will be clear to you more when we will read about the cycles and ring system. Fine. So what you have learned, that this bond will migrate on this. So in such cases, as always, I suggest don't change anything. So just one bond is formed, one bond was there here previously, and if this is forms, so if this migrates, there will be a positive charge here which will be counterbalanced by, you can consider the bond pair from here to here. Okay, so this actually it should look like this. Fine. Now we have obtained this, so let's redraw it again. So it's a 5-member ring, and along with that aldehyde. You got it? Yes. So this is the methyl magnesium bromide case. And similar thing is observed when the reagent is Grignard also, RMGX. Also Lewis isolated, because when there is an epoxide, we generally consider that, okay, epoxide means it's an Grignard reagent means it will go and attack on the epoxide and open up it to produce a 2 carbon increased alcohol. What do I say? For example, if you take ethylene oxide and if you react with Grignard reagent, so what will be the product? This is ethylene oxide plus RMGX, and this R will attack one side, means magnesium will be coordinate, R will attack, and it will produce R CH2OH. What do I mean? So it will attack here, it will open, so R is attached, so along with R there is a CH2, there is another CH2, and this is OMGBr or OMGX after hydrolysis, so H3O plus treatment, it will produce 2 carbon unit alcohol. So same thing is expected from here, but due to the same reason for this MgBr2, this is due to the same reason it produces this aldehyde. But keep it in mind, this factor. But when aldehyde is produced, then we know that aldehydes are highly reactive for the Grignard region. So this R group attacks here and opens up. So ultimately from aldehyde and Grignard, what it produces? It produces a secondary alcohol. And obviously here this is also the similar case, R, and this is H. So after workup, what is produced? So after workup, it produces this. This is OH, this is R, and it's a secondary alcohol. Okay, so this is the overall explanation of this problem. I accept that this problem is little difficult, but if you understand properly, you can solve. Okay, fine. So till now we were discussing about simple epoxide, means epoxide attached to aliphatic centers. Now we will discuss epoxide attached to aromatic centers. Okay. So in example number 5, you can see this is a epoxide made from benzene derivatives. So kept in acidic medium, and this is rearranged to this. So what is happening? Acidic medium, as said in the example, means you have to consider there are H plus, just acid, and in acidic medium doesn't mean that there should be water present. It is not essential. So this acid, so we know that, so if such type of phenomena occurs, then epoxide will definitely be protonated. Okay, so this is the H plus, this is methyl, this is. And when you have such type of problem, please be careful, cool down your brain such that you don't mistake being in hurry. So okay, fine, this is produced. So now what can happen? As there is a 2 chance. 2 chance means this side can open, this side can open. Let's think about that factor. So this is O. So one case, if this bond breaks, this is delta positive, H plus. So this and this is the methyl. And in case of another case, what could happen? This is the D, this is the H. In another case, that could be methyl, this and this bond may break. So this is the H, this is the D. So delta plus charge will be here. Okay, fine. So, okay, fine. So now you can see if you do the resonance of this structure, resonance. So what can happen? So this bond will come here. So positive charge will go here. So positive charge is here. This is the methyl, double bond. Just think that if carbocation means what I mean to say, if carbocation is generated, just let's consider the bond is broken. It will be easier for you to understand. There is a carbocation. So what can happen? This here carbocation can go here, and similarly this is D, and this is OH. This is H. Fine. This. Again another canonical structure possible here, so positive charge will come here. So what is the summary of this discussion? That for such cases, if we consider this thing, positive charge could be here, here and here. But the thing is little different from this. So in this case positive charge could be, if it comes here, if this bond comes here, what will be the structure? So this is methyl, positive charge is here. Just you can think in this way if you consider that this is broken. So this is that positive charge. So it will come, positive charge will come here. This is similarly, this is the H and this is the D. Similarly, if it goes, then positive charge will come here. Means what do I mean? That it will come and positive charge will move from here, here and here. What is the difference? Difference is that you can see that for this side, this way, the positive charge is coming on the carbon which is attached to methyl. So that is the difference between the two. Since this is on this closer to methyl, so this structure is more stable, or what do I mean? It is more capable to hold the positive charge. Is it in a proper word? This structure is more capable to hold or stabilize positive charge. Fine. So if it is more capable to stabilize the positive charge, so the corresponding energy of activation associated with this pathway will be less, and if the energy of activation is less, then the reaction rate will be faster or better or higher, whatever you say. So reaction will follow this pathway. I guess you have understood. So if it follows this pathway, then what can happen? That bond will be open from this side. So what it will result? It will produce that this is methyl, this is deuterium, this is double bond, this is plus charge is here, OH is here. Okay, and this is the H. And as we know, similar like Pinacol Pinacolone rearrangement, this is alcohol along with hydrogen, adjacent carbon is positive charge. So what can happen? So this can push, and this hydride could be migrated from here to here. Okay, understood? So if it migrates, what will be the product? If it migrates, then the product will be, this is methyl, fine, this is double bond, this is D, this is H, and here double bond. You can see this is nothing but a keto form of phenol derivative. So we know that the phenol prefers to remain in the enol form. Why? Because in enol form it has a greater resonance stabilization, means aromatic stabilization. Consequently, what happens that it will undergo enol. Now this is methyl, this is O enol. Now question is which will migrate, this H or P? That is the important question. As we know, the C-D bond is relatively stronger due to the 1 unit higher mass of this deuterium compared to H. So it is easy to break this CH bond compared to CD bond. So CH will be broken and it will result this, and there will be a double bond. So these will be the product. So in this way this product is formed. Okay, fine. So I guess we have understood this. Now we will discuss about the sixth example, where you can see there is a scrambling. Scrambling means equal spread up of that, as means target center, or you can say radioactive center here in this case. So when there is a chance, or in any question when you find that 50-50% scrambling is there, means in reaction mixture both are present in equal amount. So you have to consider one factor. Always keep it in mind. Reaction is going on through a particular intermediate. So that is the important factor. So if it goes to a particular intermediate, then there is equal chance from a particular intermediate I. It can go in this direction or it can go in this direction with a 50% probability. And this is happening here. So we will discuss now how this is happening. So this is the basic concept, background of this scrambling. So how this reaction is happening? Here in question it is mentioned that this is anhydrous acid. So keep it in mind, no water is present. Fine? Okay. So what happens here? Anhydrous acid means H plus. So oxygen has lone pair of electrons, so it will coordinate to H plus. Fine. So what it will produce? This will produce this methyl OH plus. This is methyl, and this label is actually a 14C radiocarbon. Fine. Okay. So this is the radiocarbon. So what can happen? It could have a resonance structure. I am not writing the methyl in every case. Just you keep it in mind. So it could be this bond can come here and positive charge can go to carbon, because we know it is difficult for oxygen don't like. But from basic concept point of view, in this structure every atom is octet field. So contribution of this canonical form to the overall distribution of each canonical form, this has a more contribution. Fine. So this is a carbon, this is a 6 electron center, this carbocation, 6 electron center, this is fine. So what can happen? So here positive charge is there. Fine. So simply one thing happens, that this can migrate, means there is a positive charge, so this can migrate. Fine. Or so this can migrate. So if it migrates, what will be the consequence? There will be a tertiary carbocation formation. Along with that, this is OH. Now here 2 methyl. Okay, methyl. Fine. So there is a positive charge and it's a hydroxyl. So simple chances that it may go. This is a reversible step. It may go here or there. Another what can happen? That this can be donated electron to form a epoxide. This is a methyl, this is O, this is protonated epoxide, you can see, and this is that symmetrical intermediate about what I was talking. Symmetrical intermediate. You may think that this is radio level. How this is symmetrical? Because radio level is a nuclear, radioactivity is a nuclear phenomenon. Okay, this mass of this carbon center is different. For example, normal carbon is 12 and this carbon is 14. Apart from that, this is a nuclear phenomena, and chemical reactivity is dependent on the electronic distribution of electronic phenomena. So their property is same. So this is that symmetrical intermediate. So it can follow this path to prepare this, or what can happen, that this can open. So if it opens, what will be the product? This is methyl, this is the OH, and you can see this is methyl, positive charge is here. So what can happen? It can push its electron back and this methyl can migrate. So if it is, then what will be the product? This is the methyl, this is OH plus, and here you can see 3-methyl. Fine. So and if it releases one releases one H plus, so then this right now the level is in this carbon. Fine, because level is in this carbon here, so it goes to that carbon. So in this way, absolute scrambling is obtained. Okay, fine. I guess you have understood. So now we will discuss about the last example of our discussion. And this last example, you can see it is little bit a complicated type molecule. Okay, di-tertiary butyl ketene. Fine. Ketene means means keto as well as ene. There is one double bond as well as one alkene as well as one ketone. So MCPBA is nothing but it is a metachloroparbenzoic acid. Its structure is this. This is MCPA, and this is the peroxy linkage responsible for that oxidation pathway, because in case of oxygen prefers to remain in -2 oxidation state. Here this is -1, this is -1, so that is the reason of its oxidizing capability. So what happens if it oxidizes? I'm just avoiding that to write the methyl group. Okay, so this is, and oxidizing means, if you think this is a carbonyl C double bond 1 CC, where is electron rich more? So C double bond C, this is more electron rich compared to this, because the oxygen is more electronegative. So it will prefer to keep electron on itself, means if it keep electron on itself, it is comfortable. So here electron density more, so epoxidation will occur on this center. Fine. And see, this is but a smallest lactone, 3-member lactone. Lactone is intramolecular cyclic ester. Intramolecular cyclic ester or lactone. Fine. So this is, but this is not that much stable, because 3-member ring, first point it's a 3-member ring, and second point, one member of this 3-member ring, this is a sp2 carbon. So we know, because sp2 carbon prefers 120-degree angle, 120 degree, here it is around 60 degree, so not stable, strained. So what happens? It opens up, and another driving force for this opening is the consequence. What do I mean? See, if it is opens up, there is a positive charge, this and this is O minus. Fine. And we know this positive charge is nothing but it's a tertiary carbocation, so relatively stable. Okay, fine. So that's why these will form very easily. This is methyl. So there are 2 tertiary butyl groups, so 6 methyl possible. Let's consider one. Means this methyl can migrate, since it's a carbocation. So if it migrates, what will be the product? So this is methyl, carbocation is here. So this is the tertiary butyl, this is 3-methyl, and here is 1-methyl which is migrated. This is a migrated methyl. Okay, this is a migrated methyl group. So okay, fine. Now the question, what is the driving force? Why they will? Which answer you get now? So now it can attack here and form a 4-member ring. See this. If it attacks, this will be formed. Now the reason, release of ring stain. Release of ring strain. From this around 60 degree to this is around 90 degree. So that is the 90, not centrigrade. This is about 90 degree. So this is the reason why this reaction will go and end up here. So in this way, this reaction happens. And what is the fate of this MCPBA? This is a simple ClCOOH. Fine. Oh, so this is the end of this discussion. So what we have learned today? We have learned that this epoxide can also perform this Pinacol Pinacolone rearrangement because chemically they are almost similar to the epoxide diol, 1,2-diol, because they are the dehydrated form of diol and they can perform the same process not only in presence of acid but they can form these in presence of Lewis acid, and that Lewis acid could be BF3 ether, could be magnesium 2 plus, like that, and they can undergo various reaction, even they can undergo rearrangement. Okay, so we have learned all these examples. So I hope you have enjoyed this teaching. So if you like my teaching, please support my channel, and how you can share these videos among your friends such that many people could be benefited, and I'll be very happy that if many people could be benefited from my effort. And finally, subscribe my channel Chemistry the Mystery of Molecule, and share, comment on this video, and most importantly, please press the bell icon to get the notification of every single video I upload. So stay happy, stay cool, see you in my next video.